As you've seen, a polynomial is made up of polynomial terms, which consist of a numerical coefficient, a variable, and an integer power greater than or equal to 0. What do graphs of polynomials look like? Let's take a look at these polynomial graphs. First, by looking at just the graphs of the individual polynomial terms and then combinations of them. Our goal is to see if all polynomial graphs are also graphs of functions. Briefly, a function is a rule that takes an input value and outputs a unique value. This is often represented by what is termed a function machine. The graph of a function passes the vertical line test. This means that if a vertical line intersects the graph at only one point, anywhere along the graph, then it is a function. So, let's look at graphs of functions of this form. We'll look at values of k from 0 to 6. For simplicity, we'll let a equal 2. The first graph, then, is y equals 2. The reason there is no x term is because when k equals 0, then x to the 0 power is 1. The graph of y equals 2 is a horizontal line, and it is a function. It passes the vertical line test. The next graph is for k equals 1, which results in y equals 2x. This is the graph of a linear equation, and from your previous study of linear graphs you know that these, in fact, are functions. The next graph is for k equals 2, which results in y equals 2x squared. From your study of quadratics, you know that these are also functions. The next graph is for k equals 3, which results in y equals 2x cubed. Cubics of this form are also functions. The next graph is for k equals 4, which results in y equals 2x to the 4th power. Notice how this graph looks similar to a quadratic. Not all 4th power graphs look like this, but graphs of this sort are functions. The next graph is for k equals 5, which results in y equals 2x to the 5th power. Notice how this graph looks similar to the cubic function shown earlier. Not all 5th power graphs look like this, but graphs of this sort are also functions. Finally, we have the graph of k equals 6, which results in y equals 2x to the 6th power. Once again, we notice the parabolic shape of this type of graph. Although not all 6th power graphs look like this, graphs of this sort are also functions. A polynomial function is written this way, as the sum of polynomial terms. The value of n determines the degree of a polynomial. This is an example of a third-degree polynomial. It has a cubic term, a quadratic term, a linear term, and a constant term. We've seen how each of these separate terms are themselves a function. So, is the sum of these 4 functions also a function? Here is the graph, and as you can see it behaves like a function. But how can we be sure that this is true for any polynomial? Let's look at an example of adding 2 third-degree polynomials with letters for coefficients. Both f of x and g of x are polynomial functions. Let's add them to create a third function h of x. Notice how the coefficients for the x terms are factored out and form a single coefficient. In fact, we can replace the sum of the 2 coefficients and call it by a new label, using the letter c. You can see that h of x is clearly a function because it is another polynomial. We can generalize this for n terms to get these versions of f of x, g of x, h of x. This shows that the sum of any 2 polynomial functions is another polynomial function. This means that the graph of any polynomial function passes the vertical line test. This shows a quadratic trinomial with continuously changing values for the coefficients. As you can see from the graphs, these are all functions. The graph of a polynomial function can intersect the x-axis. When that happens is an indication of being able to factor the polynomial. For example, here is the graph of the function x cubed minus 9x squared plus 20x minus 12. Notice that it intersects the x-axis at x equals 1, 2, and 6. This cubic function can be rewritten in this form. Try graphing both forms of the cubic function on a graphing calculator. you'll see the graphs are identical. Notice that each factor is a linear binomial. Watch what happens when we graph the linear binomials overlaid on the cubic. Each linear binomial intersects and crosses the x-axis. The same thing happens with the polynomial graph. Now let's look at another polynomial that has those same three roots. Notice the difference? The factor with the binomial x minus 1 is squared. Let's look at what happens to the polynomial graph near this x-intercept. Here is a close-up. Rather than cross over the x-axis, the graph seems to bounce off. Why does this happen? Look at the graph of the corresponding binomial squared. When a linear binomial factor is raised to an even power, you'll see this kind of behavior. Here is the graph of that same binomial raised to the fourth power. Now let's look at odd-numbered powers. With this graph you see the linear binomial x minus 2 raised to the first power, which is an odd power. Now let's look at the graph with that same binomial cubed. Notice that the cubic function crosses over the x-axis, but not the way that it did with the binomial to the first power. Let's overlay the cubed binomial to account for this behavior. At x equals 2, the graph goes through a subtle twist. The point on the x-axis is called an inflection point. There would be a similar inflection point for higher odd powers of the binomial. When a binomial factor is raised to a power, the numerical value of that power is known as the multiplicity of the factor. As you saw, the type of multiplicity leads to a different behavior for the polynomial curve. To summarize, when a polynomial graph intersects the x-axis, it can do so in three ways. 1. It can cross over the x-axis, indicating a linear factor. 2. It can bounce off the x-axis, indicating a factor with an even power. 3. It can twist through an inflection point, indicating a factor with an odd power. Let's use this polynomial behavior in an example. Here is part of a roller coaster. The shape is modeled by a polynomial that has the factors shown based on the x-intercepts. The polynomial is of degree 6. The first part of the graph has a multiplicity of 1. The second part has a multiplicity of 3. The third part has a multiplicity of 2. What is the polynomial function? Using the information provided in the graph, we can construct the following 6-degree polynomial with the given x-intercepts. Test it out on a graphing calculator. Let's look at a final example. Here is another portion of a roller coaster. It is also modeled by a 6-degree polynomial. Given the x-intercepts shown, find the polynomial function. Given the x-intercepts, we know the polynomial is going to be the product of these three linear factors. Now we need to account for the multiplicities. Analyze the graph. We end up with these multiplicities. The resulting function, accounting for the multiplicities, is shown here.